gravity is the most familiar force in the universe and also the most misunderstood. Every moment of your life you feel it pulling your body toward the ground, keeping your feet planted on the surface of this planet as it spins through space. Every breath you take depends on it, because gravity holds the air close enough to breathe. Every sunrise exists because gravity keeps this world circling our star, the sun, in a delicate balance that has lasted for billions of years. Yet when physicists measure gravity and compare it to the other forces of nature, they discover something deeply unsettling. Gravity is unimaginably weak. Two tiny particles called electrons repel each other with a force that is about 10 to the power of 38 times stronger than the gravitational attraction between them. This number is so enormous that it defies intuition. If gravity were just a little bit stronger, stars would collapse in on themselves almost instantly. If it were a little weaker, galaxies would never form. But in the realm of the very small, gravity barely exists at all. It is drowned out by every other interaction, as if it were a whisper in a room filled with thunder. This imbalance is not just strange, it is one of the deepest unsolved problems in all of physics. Scientists call it the hierarchy problem. The word hierarchy here means that the forces of nature seem to be arranged in layers of strength that make no obvious sense. Electromagnetism and the nuclear forces are incredibly strong, yet gravity is separated from them by an enormous gap that no current theory can naturally explain. There is no equation in known physics that demands gravity must be so weak. It simply appears that way when we measure it, and that is deeply suspicious. For decades, physicists tried to solve this puzzle by tweaking equations, adding new particles, or inventing new symmetries of nature. But every attempt ran into the same wall. Nothing inside the known universe could easily account for why gravity is so feeble. It was as if something important was missing from the picture. Then a radical idea began to take shape. What if gravity is not actually weak at all? What if it only appears weak because it is leaking away from our universe? Imagine pouring a cup of ink into a single glass of water. The ink would look dark and concentrated, but pour that same cup into an ocean, and it would become so diluted that you might never notice it at all. The total amount of ink has not changed, but its spread has. Some physicists began to wonder if gravity might be doing something similar. Perhaps it is spreading out into spaces we cannot see. This idea sounds like science fiction, but it grew out of very real mathematics. The equations of modern physics do not forbid the existence of extra dimensions of space beyond the three we experience. In fact, some of the most advanced theories we have require them. If gravity is allowed to move through these hidden dimensions while all other forces are trapped in our familiar three-dimensional world, then gravity would appear weak to us because most of it would be flowing somewhere else. This would mean that the true strength of gravity could be just as powerful as the other forces, but we only feel a faint shadow of it. The rest would be spreading through a larger cosmic arena that we cannot directly observe. This idea transforms the hierarchy problem from a mystery into a clue. The weakness of gravity might not be telling us that gravity is special. It might be telling us that space itself is bigger than we ever imagined. And if that is true, then our universe might not be a closed box at all. It could be more like a surface, floating in a much larger reality. A reality where gravity can wander freely, slipping into regions that lie beyond the reach of light, matter, and even time as we know it. That possibility changes everything. It suggests that the structure of reality is far deeper than the stars we see in the night sky. It hints that there may be hidden dimensions wrapped around every point in space, silently carrying away a force that binds the cosmos together. Gravity might not be weak, it might simply be reaching farther than we can see. Gravity is not just a force, it is the architecture of reality itself. It tells planets how to move, stars how to burn, and galaxies how to form their immense spirals across the darkness. It shapes the fabric of space and time, bending them in ways that allow clocks to tick and light to travel. Yet when scientists look at the equations that describe gravity, something feels incomplete. The laws that govern electromagnetism and the nuclear forces fit neatly into a framework called quantum theory. Gravity refuses to fit. It remains stubbornly classical, described by Albert Einstein's theory of general relativity, a theory that works beautifully for large objects, but breaks down when pushed to the smallest scales. This mismatch is not a small technical problem. It is a sign that our understanding of the universe is fractured. Quantum theory tells us how particles behave, how energy jumps in discrete steps, and how uncertainty is woven into the heart of nature. General relativity tells us how space and time curve, how mass and energy sculpt the geometry of the cosmos. Both theories have been tested with extraordinary precision. Both are astonishingly successful, yet when they are brought together, they clash. One reason this clash is so severe may be tied directly to the weakness of gravity. Because gravity is so faint at small scales, its quantum effects are almost impossible to observe. The energy required to probe gravity at the level of individual particles is so enormous that it lies far beyond anything humanity can currently achieve. This has left physicists with a frustrating gap in their knowledge, a place where the equations go silent. But if gravity is leaking into hidden dimensions, then its weakness is not fundamental. It is a side effect of geometry. The true gravitational force might be as strong as the others, but it is spread across a vast multidimensional space. What we measure is only the tiny fraction that remains confined to our three-dimensional world. To see how this works, imagine standing on a long, narrow road at night with a single lamp. If the road were one-dimensional, just a line, the light would spread only forward and backward. It would stay bright for a long distance. But if the same lamp were placed in an open field, the light would spread in all directions. It would fade much more quickly. The lamp has not changed, only the space it can fill. Gravity may be doing the same thing. In a universe with extra dimensions, gravitational influence could spread outward into directions we cannot perceive. As it does, it would weaken in our familiar three-dimensional space, just as the light fades when it spreads across a larger area. This idea offers a stunningly simple explanation for a problem that has haunted physics for generations. The hierarchy problem no longer requires exotic particles or fine-tuned equations. It emerges naturally from the shape of space itself. Yet this solution comes with a profound implication. If gravity can move into extra dimensions, then our universe might not be isolated. It could be part of a larger structure, sometimes called the bulk, within which our visible cosmos is just a thin slice. In this picture, everything we know, every star, every planet, every living thing, exists on a kind of cosmic surface. This surface is often called a brane, a word that comes from membrane. It is a three-dimensional space floating inside a higher dimensional reality. Light, matter, and all the forces we experience except gravity are trapped on this brane. They cannot leave it, but gravity can. This means that gravity is a messenger from beyond our universe. It is the only force that can travel through the deeper layers of reality. Every time you feel your weight, every time a planet curves around a star, you may be experiencing the influence of dimensions that lie far outside the reach of your senses. If this is true, then the universe is not just vast, it is layered. What we see is only the surface of a much greater structure. The weakness of gravity may be the whisper of a hidden world. If gravity is truly free to wander beyond our universe, then it carries with it information about realms we cannot see. Every gravitational pull is not just an interaction between masses. It is a tiny echo of a deeper geometry. The planets orbit the Sun, not only because of the mass of the star, but because space itself is curved in a way that may extend far beyond the three directions we experience. That curvature might ripple through hidden dimensions, subtly altering the way gravity behaves. Physicists have searched for any sign that gravity does not follow the familiar inverse square law, the rule that says its strength falls with the square of the distance. In a universe with only three dimensions of space, this law must hold exactly. But in a universe with more dimensions, gravity would spread out more quickly, and the law would change at very small distances. Detecting such a change would be one of the clearest signs that extra dimensions exist. So far, every experiment has confirmed the inverse square law down to extremely tiny scales. But the smallest distances we can test are still far larger than the realm where these hidden dimensions might be hiding. The door remains open. This uncertainty is what makes the mystery of gravity so powerful. It sits at the boundary between what we know and what we do not. It touches the smallest particles and the largest structures at the same time. It may even connect our universe to others. When scientists look at the equations of theories that include extra dimensions, something remarkable happens. The numbers begin to line up. The enormous gap between gravity and the other forces can emerge naturally, without any artificial adjustments. The universe no longer looks like a finely tuned accident. It looks like a consequence of a deeper design. Yet there is a price for this elegance. It requires that reality be far more complex than it appears. It requires dimensions that are invisible, spaces that we can never enter, and perhaps even other universes that exist alongside our own. These ideas are not proven. They remain hypotheses, built from mathematics and constrained by experiment. But they are not fantasy. They arise from the most advanced attempts to unite gravity with the quantum world. They are taken seriously because they solve problems that nothing else can. The weakness of gravity is not a minor detail. It is a crack in the foundation of physics. Through that crack, we may be glimpsing a far larger cosmos. Perhaps gravity is not weak because it is insignificant. Perhaps it is weak because it is doing something extraordinary. Perhaps it is holding together not just our universe, but many. This is where the journey begins. Space feels empty, but it is not simple. Every direction you can point your finger defines a dimension. Left and right is one, forward and backward is another, up and down is a third. These three directions are so deeply woven into human experience that it is difficult to imagine anything beyond them. Time adds another dimension, one that carries us from past to future, but even time follows rules that feel familiar. What lies beyond these four is something entirely different. More than a century ago, physicists began to wonder if extra dimensions might exist, curled up so tightly that we never notice them. The idea was first explored by Theodore Kaluza and Oscar Klein, who discovered that if space had one extra dimension beyond the three we know, the equations of gravity would naturally produce electromagnetism. Two forces that had seemed unrelated suddenly became aspects of the same geometry. Gravity and electricity emerged from the shape of space itself. This was not just a clever trick, it was a profound insight. Forces might not be fundamental. They might be shadows of higher dimensional motion. In the Kaluza-Klein picture, the extra dimension is wrapped into a tiny loop at every point in space, so small that even the smallest particles cannot move through it in any noticeable way. To us, the universe looks three-dimensional, but deep down, it is richer. Decades later, this idea returned in a more powerful form through string theory. In this framework, the basic building blocks of reality are not point-like particles, but tiny vibrating strings. Each vibration corresponds to a different particle, much like different notes played on a violin string. For the mathematics of these strings to be consistent, the universe must have more than 3 dimensions of space. In most versions of the theory, there are 10 or even 11 dimensions in total. These extra dimensions are not optional, they are required. Without them, the equations break down. The theory loses its internal harmony. The reason we do not see these dimensions is that they may be curled up into incredibly small shapes, far smaller than an atom. Each point in space could contain a tiny complex geometry, folded in on itself like an intricate knot. Particles moving through this hidden geometry would give rise to the properties we observe, such as mass and electric charge. Yet some physicists realize something even more astonishing. The extra dimensions do not all have to be tiny. Some of them could be large, perhaps even as large as a fraction of a millimeter. They could be hidden not because they are small, but because ordinary matter cannot enter them. This is where gravity becomes special. If all particles were confined to a 3-dimensional brane, a surface within a higher dimensional bulk, then they would never feel these extra dimensions. They would behave exactly as if space had only 3 dimensions. But gravity, being a distortion of space itself, would not be confined. It could spread into the bulk. This would make gravity look weak to us, because most of its influence would be leaking into directions we cannot access. The universe might be far more spacious than it appears. What we call reality could be just a thin layer within something vastly larger. If extra dimensions exist, they are not empty. They are part of the fabric of space itself, just as real as the 3 directions you move through every day. The reason you cannot step into them is not because they are unreal, but because the forces that make up your body are confined. Every atom, every electron, every quark is bound to the 3-dimensional brane that defines our universe. These particles are like ink trapped on a page. They can move freely across the surface, but they cannot leave it. Gravity is different. It is not made of particles in the usual sense. It is the curvature of space and time. When mass and energy are present, they tell space how to bend, and that bending tells matter how to move. If space has extra dimensions, then gravity automatically extends into them. It has no choice. This leads to a beautiful and unsettling picture. Our universe is a kind of island in a higher dimensional ocean. Light cannot leave it. Matter cannot leave it. Even the strong and electromagnetic forces are tied to it. But gravity flows through the entire ocean, connecting every island that might exist. If there are other brains, other universes floating in the same bulk, gravity could be the only force they share. They would be invisible to us, yet their mass could still tug on our space, influencing the motion of galaxies in subtle ways. This idea has been explored in a class of theories known as brain world models. In these models, the laws of physics we observe arise because our universe is a brain embedded in a higher dimensional space. The extra dimensions can be shaped in different ways. Some may be tightly curled. Others may stretch out, forming vast hidden directions. One particularly influential version is known as the Randall-Sundrum model. It shows that even if an extra dimension is infinitely large, gravity can still be localized near our brain, becoming weaker as it moves away. This creates a natural hierarchy between gravity and the other forces. The geometry of the extra dimension itself acts like a gravitational trap. In this picture, gravity is strongest near our universe and fades as it moves deeper into the bulk. We feel only the part that remains close. The rest escapes. This escape does not violate any known law. It is a direct consequence of Einstein's equations when they are extended into higher dimensions. The math allows it. The physics permits it. What this means is that the weakness of gravity might not be a flaw in our theories. It might be a window into a larger reality. The universe may not be a self-contained arena. It may be an interface. Every gravitational pull could be a tiny interaction with the unseen. The existence of hidden dimensions changes the meaning of distance itself. 2 points that appear far apart in our three-dimensional space might be close together in the higher dimensional bulk. This opens the door to phenomena that seem impossible from our limited perspective. Gravity could take shortcuts through these extra directions, altering how it spreads and how it connects different regions of space. If this is true, then the universe we see is only a projection of something much richer. The stars, the galaxies, the vast cosmic web are patterns on a surface. Beneath that surface lies a deeper structure that shapes everything we observe. Scientists have searched for signs of these extra dimensions in many ways. Particle accelerators look for evidence that energy can leak into hidden directions. If extra dimensions are large enough, collisions at very high energies could produce particles that vanish from our universe, carrying momentum away into the bulk. So far, no such events have been confirmed, but the limits grow tighter with every experiment. Gravity itself provides another test. If it spreads into extra dimensions, then at very small distances, it should deviate from the inverse square law. Precision measurements of gravitational attraction between small objects have pushed these tests to remarkable accuracy. They show that if extra dimensions exist, they must be smaller than a tiny fraction of a millimeter, or shaped in a way that hides their effects. Yet even such small dimensions could have enormous consequences. A single extra dimension, just a little larger than the Planck length, could be enough to change the fundamental strength of gravity. A handful of extra dimensions could transform the entire structure of physics. The idea that matter is trapped while gravity is free is one of the most elegant concepts in modern theoretical physics. It explains why we do not see extra dimensions in everyday life, while still allowing them to exist. It also explains why gravity is so weak without invoking arbitrary numbers. The universe becomes a place of layers. Our reality is one layer among many, and gravity is the thread that passes through them all. The universe is no longer a single isolated arena. It is a surface floating inside something larger. This idea is called the brain world hypothesis, and it takes everything we know about reality and places it on a thin cosmic membrane. Every star, every atom, every thought exists on this membrane, which drifts through a higher dimensional space known as the bulk. The word brane comes from membrane, and it is used to describe a space that has 3 dimensions of extension but is embedded in a space that has more. Just as a 2-dimensional sheet of paper can exist within a 3-dimensional room, our 3-dimensional universe could exist within a higher dimensional cosmos. The paper feels complete to the ink drawn on it, but it is only part of a larger reality. In this picture, all the forces and particles we know are confined to the brain. Electrons, photons, quarks, and even the forces that bind them together are like patterns drawn on the surface. They cannot leave. They cannot fall off the edge. Their entire existence is defined by the geometry of the brain itself. Gravity is the exception, because gravity is the curvature of space and time. It is not limited to the brain. It can propagate through the bulk. When a star forms, it bends not only the space of our universe, but also the surrounding higher dimensional space. That bending spreads outward, weakening as it goes, just as ripples fade across the surface of a pond. This explains something extraordinary. If gravity spreads into extra dimensions, then only a small part of its strength remains on the brain. We feel that small part as the feeble force that governs falling apples and orbiting planets. The rest of gravity is out there, moving through dimensions we cannot see. In this view, gravity is not weak because it is different from the other forces. It is weak because it has more room to roam. This idea has been developed in many mathematical models. Some of the most famous show that the bulk can warp space in such a way that gravity becomes concentrated near the brain. It is strongest where we live and fades away as it moves outward. This keeps gravity from disappearing entirely, while still allowing it to escape enough to appear weak. The brain-world hypothesis offers a new way to think about existence itself. Our universe may not be everything. It may be a region, a layer, a domain within a greater whole. Other brains could exist nearby, each carrying its own universe, with its own particles and forces. We would never see them directly. Light and matter cannot cross the gap, but gravity might. If so, then the mass of other universes could influence ours. Their galaxies could tug on our space. Their black holes could distort our geometry. We would feel their presence only through subtle gravitational effects, like whispers from a hidden world. The cosmos becomes a crowded place, not in the sense of visible objects, but in the sense of layered realities, and our universe may be just one of them. If our universe is a brain, then its thickness may be far smaller than anything we can imagine. It could be thinner than an atom, thinner than a proton, thinner even than the smallest length that quantum physics normally allows. To us, it feels infinitely thin, because everything we are made of is confined within it. There is no way to step off it. There is no direction that leads away from it. The extra dimensions are not sideways or upward. They are orthogonal to everything we know. Yet gravity feels them. When a massive object like a star or a planet exists, it warps the brain and also warps the bulk around it. That warp can leak away from our universe, carrying gravitational influence into higher dimensions. This leakage is what makes gravity fade so quickly with distance compared to the other forces. The mathematics of brain-world models show that this leakage is not random. It follows precise geometric rules. In some models, the bulk has a special curved shape that pulls gravity back toward the brain, preventing it from escaping completely. In others, gravity can wander farther, weakening more rapidly as it spreads. This balance is delicate. If gravity leaked too much, our universe would not hold together. Stars would not form. Galaxies would drift apart. The fact that complex structures exist tells us that if extra dimensions are real, their geometry must be finely tuned to allow gravity to remain just strong enough where we live. This does not mean the theory is artificial. It means that the shape of the bulk matters. Just as the shape of space around a black hole determines how matter moves, the shape of higher dimensional space determines how gravity behaves in our universe. In some brain-world models, the bulk can be vast, even infinite. Our brain floats within it, like a sheet in a limitless ocean. In others, the bulk is compact, wrapped into a complex form that stabilizes the brain. Both possibilities are allowed by the equations. What matters most is that gravity alone has access to this hidden arena. It is the only force that can feel the full dimensionality of reality. This gives gravity a unique role. It is not just the force that pulls objects together. It is the force that connects our universe to everything beyond it. Every gravitational interaction becomes a potential bridge between worlds. If gravity truly moves through the bulk, then it carries energy away from our universe. This loss would be incredibly small, far too subtle to notice in everyday life. But over cosmic distances and over billions of years, it could shape the fate of the universe itself. Gravity might slowly drain into higher dimensions, altering how structures form and how space expands. This possibility has led physicists to ask a haunting question. Could gravity escape entirely? In some brain-world scenarios, gravity is bound to the brain only loosely. It can hover near it for a time, but it is not permanently trapped. Over long periods, gravitational energy could diffuse into the bulk, weakening the gravitational bonds that hold galaxies and clusters together. If this is happening, then the large-scale behavior of the cosmos might carry the signature of hidden dimensions. The universe might expand faster than expected. Matter might clump less tightly than predicted. Dark energy, the mysterious force that seems to be driving cosmic acceleration, could in part be an illusion caused by gravity leaking away. This does not mean that dark energy is explained by extra dimensions. Many competing theories exist, but the possibility is real enough that it has been studied seriously. The equations allow it. The observations do not yet rule it out. The brain-world hypothesis transforms gravity from a simple force into a cosmic messenger. It tells us not only about the mass and energy in our universe, but about the shape of the space beyond it. If gravity is escaping, then our universe is not a closed system. It is exchanging energy with a larger reality. The walls of the cosmos may be porous, and gravity may be the only thing that can slip through. It is one of the most daring concepts in modern physics. It takes a force that seems gentle and familiar and reveals it as a traveler through realms we cannot see. To understand how this leakage could happen, physicists imagine gravity as being carried by tiny quantum messengers called gravitons. These hypothetical particles are to gravity what photons are to light. They carry the influence of mass and energy through space and time. In a universe with extra dimensions, these gravitons would not be confined to our three-dimensional brain. They would be free to wander into the bulk. When a star forms, or a planet gathers its mass, it sends out a flux of gravitons. Some of them remain close to our universe, binding matter together and shaping orbits. Others slip away into higher dimensions. From our point of view, those gravitons are lost. The gravity they carry no longer contributes to the pull we feel. This is what makes gravity appear so weak. The effect is subtle but profound. At large distances, gravity behaves almost exactly as Einstein predicted. The inverse square law holds. The force weakens with the square of the distance. But at very small scales, or in regions where the geometry of extra dimensions becomes important, this law could change. Gravity might weaken faster than expected because more of it is leaking away. Physicists have searched for this effect with delicate experiments. They measure the gravitational attraction between small masses separated by tiny distances, looking for any deviation from the inverse square law. These experiments are incredibly difficult. Gravity is so faint that even the slightest vibration or temperature change can overwhelm the signal. Yet, over the years, scientists have pushed these measurements to remarkable precision. So far, no deviation has been found. This tells us that if extra dimensions exist, they must be small or shaped in a way that hides their influence. But it does not rule them out. The hidden dimensions could be curled up just beyond our reach, or warped in a way that traps gravity close to our brain. In some models, gravity does not leak uniformly. It may linger near our universe for a time, before drifting away. This creates a kind of gravitational halo around the brain, a region where gravity is strong and familiar. Beyond that region, in the deeper bulk, gravity fades. We live inside this halo, unaware of the vast space beyond. This picture makes a striking prediction. If gravity can escape, then some gravitational energy should be missing from our universe. We would not notice this loss in everyday life, But in extreme events, such as the collision of black holes or the birth of neutron stars, it might become detectable. These events release enormous amounts of gravitational energy. If some of that energy vanishes into extra dimensions, the signals we observe would be weaker than expected. This is why gravitational wave detectors are so important. They allow us to listen to the universe in a new way, to hear the ripples in space and time as massive objects collide. These ripples are carried by gravity itself. If gravity leaks, then gravitational waves might also leak. They could fade faster than predicted as they travel through space. By studying these waves, physicists hope to test the very fabric of reality. They look for any sign that the waves lose energy in a way that cannot be explained by ordinary physics. So far, the data matches Einstein's theory with astonishing accuracy. But the measurements are still improving. Each new detection sharpens our view. The possibility of leaking gravity also touches the deepest questions about the universe. If gravity can escape, then the total energy of our cosmos is not fixed. It can flow into the bulk, changing the evolution of space itself. This could influence the expansion of the universe, the formation of galaxies, and even the ultimate fate of everything we know. What began as a solution to the hierarchy problem becomes a gateway to a far richer picture of existence. Our universe may be open, not closed. It may be exchanging gravitational influence with something far greater. Gravity might be the only force that knows what lies beyond. When gravity leaks into extra dimensions, it does not vanish in a dramatic way. It diffuses. Just as heat spreads from a hot object into cooler surroundings, gravitational influence can spread from our brain into the bulk. The equations that describe this process come from extending Einstein's theory into higher dimensions. In these equations, space is not just curved by mass, it is connected across multiple layers of geometry. The bulk acts as a reservoir where gravitational energy can flow. One of the most intriguing consequences of this is the possibility that gravity becomes weaker over time. If a tiny fraction of gravitational influence is always escaping, then the effective strength of gravity within our universe could slowly decline as the cosmos ages. This effect would be extremely small, far too subtle to notice in the motion of planets or stars. But on the scale of billions of years and billions of light years, it could matter. Galaxies might not bind as tightly as they once did. Clusters of galaxies might slowly loosen. The cosmic web that stretches across the universe could become more fragile. These changes would be almost invisible in any single moment, but they could shape the long-term evolution of the cosmos. This idea has even been proposed as a possible contributor to the mysterious acceleration of cosmic expansion. Astronomers have discovered that the universe is not just expanding, it is expanding faster and faster. Something is pushing space apart, overcoming the pull of gravity. This unknown influence is called dark energy. No one knows what it is. If gravity is leaking away, then its ability to slow the expansion of space would weaken. The universe would appear to accelerate, even if no exotic energy were present. The expansion would not be driven by a mysterious force, but by the gradual loss of the one force that holds everything together. This does not mean that dark energy is explained by gravity leakage. The data can be interpreted in many ways, but the possibility remains open, and it shows how deeply extra dimensions could be entwined with cosmic history. The mathematics of these models reveals something else as well. The bulk does not have to be empty. It can contain its own fields and structures. These could interact with gravity as it moves through them, further altering how gravity behaves on the brain. In some scenarios, the bulk could even contain other brains, other universes, each with its own physics. Gravity would then be a kind of universal language. It would be the only way these separate realities could influence one another. Their masses would tug on our space. Our masses would tug on theirs. A silent conversation would unfold across dimensions. Every gravitational pull you feel could be a superposition of influences from beyond your universe. The cosmos might be far more crowded than it appears. If gravity truly moves through higher dimensions, then black holes become especially important. These are the most extreme concentrations of gravity in the universe. They warp space and time so strongly that even light cannot escape. In a brain world picture, a black hole does not just curve our three-dimensional brain, it also creates a deep well in the bulk That well could act as a channel through which gravity flows more freely into hidden dimensions. Some models predict that black holes on a brane might be connected to higher dimensional objects in the bulk. These are sometimes called black strings or black branes. They extend beyond our universe, threading through the extra dimensions. From our perspective, we see only the part that intersects our brane, but in the bulk, the structure could be far larger. If this is true, then black holes could be gateways through which gravitational energy escapes most efficiently. They might drain gravity from our universe at a rate far higher than ordinary matter does. Over cosmic time, this could subtly alter the balance of forces that shape galaxies and clusters. This idea also changes how black holes evaporate. According to quantum theory, black holes emit a faint glow known as Hawking radiation. This radiation slowly carries energy away, causing the black hole to shrink. In a universe with extra dimensions, some of this radiation could leak into the bulk. Black holes might evaporate faster than predicted. Their lifetimes would be shorter. Their final explosions might be dimmer in our universe than expected. Physicists have searched for any sign of such behavior. They look at the masses of black holes, the distribution of their sizes, and the gravitational waves produced when they collide. So far, everything agrees with ordinary four-dimensional physics, but the uncertainties are still large. Subtle effects could be hiding within the noise. The search for leaking gravity is not a quest for fantasy. It is a test of the deepest structure of reality. If even a tiny fraction of gravity escapes our universe, it would mean that space is larger than we thought. It would mean that our cosmos is embedded in something greater. We would no longer be living in a closed universe. We would be living on a cosmic shoreline, and gravity would be the tide that moves between worlds. One of the greatest discoveries in science. When astronomers look at distant galaxies, they see that space itself is stretching, carrying those galaxies away from us. At first, scientists believed that gravity should slow this expansion over time. The mass of all the stars and galaxies should pull everything back together, gradually reducing the outward motion. But the universe did something unexpected. Observations of distant supernovae revealed that the expansion is accelerating. Galaxies are not just drifting apart, they are speeding up as they go. Some invisible influence is overpowering gravity on the largest scales. This unknown influence is called dark energy, and it makes up most of the energy in the universe. No one knows what dark energy is. It could be a property of empty space itself. It could be a new kind of field that fills the cosmos. Or it could be a sign that our understanding of gravity is incomplete. If gravity is leaking into extra dimensions, then its ability to counteract cosmic expansion would weaken over time. The universe would appear to accelerate, even if no mysterious energy were present. Space would stretch more easily as gravity slowly lost its grip. In this picture, dark energy is not something that pushes the universe apart. It is something that fails to pull it back together. The acceleration becomes a symptom of gravity's escape. The equations of brane-world cosmology show that this is mathematically possible. When gravity can flow into the bulk, the effective strength of gravity on the brane changes. The expansion of space responds to this change. Under certain conditions, the universe can enter a phase of accelerated expansion without any exotic energy at all. This does not mean that dark energy is solved. Many models exist, and most fit the data just as well. But the idea that hidden dimensions could be responsible is one of the most intriguing possibilities. It means that the fate of the universe could be shaped by what lies beyond it. If gravity continues to leak away, then galaxies may eventually drift too far apart to interact. Stars will burn out. Black holes will evaporate. The cosmos will grow cold and empty. This bleak future is known as heat death, and it may be hastened by gravity loss. Yet there is also a more subtle implication. If gravity connects our universe to others, then the energy we lose may not be gone. It may be flowing into neighboring branes. Their universes could be gaining gravitational influence as ours loses it. A grand exchange could be unfolding across dimensions. The expansion of our universe might be part of a much larger cosmic cycle. When astronomers map the large-scale structure of the universe, they see a vast network of galaxies and dark matter stretching across billions of light years. This cosmic web formed because gravity pulled matter together after the Big Bang. Tiny fluctuations in the early universe grew into galaxies, clusters, and filaments under the influence of gravity. The strength of that pull determined how quickly structures formed and how tightly they bound. If gravity has been slowly leaking into extra dimensions, then the growth of this structure would be altered. In the distant past, when the universe was young, gravity might have been slightly stronger. Matter would have clumped more efficiently. As time passed and gravity leaked away, the formation of new structures would slow. The cosmic web would become more diffuse. This effect could leave an imprint on the distribution of galaxies we observe today. Subtle differences in how matter is arranged could reveal whether gravity has changed over time. Astronomers have begun to look for such signatures, comparing precise maps of galaxy clustering with predictions from different theories. So far, the results are consistent with ordinary gravity, but the uncertainties are still large. The data does not yet rule out a small amount of gravitational leakage. The universe is a noisy place, and the signals we seek are faint. The cosmic microwave background, the afterglow of the Big Bang, offers another window. This ancient light carries information about the early universe, when it was only a few 100,000 years old. The patterns in this radiation depend on how gravity behaved at that time. If gravity were stronger or weaker than expected, the pattern would change. Measurements from satellites have shown remarkable agreement with the standard model of cosmology. But even here, there is room for slight deviations. A tiny shift in gravity over billions of years could still be hiding within the data. The search for gravity loss is therefore a game of precision. It requires not just better theories, but better measurements. Each improvement narrows the range of possibilities. What makes this quest so profound is that it links the fate of the universe to its geometry, the expansion of space, the formation of galaxies, and the destiny of everything that exists may depend on dimensions we cannot see. The universe might be evolving not only because of what is inside it, but because of where it is embedded. If gravity is escaping our universe, then the ultimate fate of the cosmos could be very different from what we expect. In standard cosmology, gravity continues to act forever, even as the universe expands. Galaxies drift apart, but within each galaxy stars and planets remain bound. Structures endure even in a cold and empty future. But if gravity weakens over time, those bonds could eventually break. Galaxies might slowly dissolve. Stars could drift away from one another. Even the orbits of planets might become unstable over unimaginably long timescales. The universe would not just grow empty, it would unravel. This scenario is speculative. There is no evidence yet that gravity is changing in this way, but it is allowed by the mathematics of extra-dimensional theories. The equations do not forbid it. They simply say that if extra dimensions exist and gravity can move through them, then gravity on the brane is not guaranteed to be constant. The idea that the fate of our universe depends on its connection to something larger is both unsettling and awe-inspiring. It means that we are not isolated. We are part of a greater structure whose dynamics we barely understand. Dark energy, cosmic acceleration, and the long-term destiny of everything we know may be linked to hidden dimensions. Gravity may be telling us a story that spans more than one universe. Expressions of gravity in the universe. They are not merely massive objects. They are regions where space and time are bent so deeply that the ordinary flow of reality breaks down. When a star, many times more massive than our Sun, exhausts its nuclear fuel, it can no longer support itself against its own weight. The core collapses inward, crushing matter to densities far beyond anything that can exist elsewhere. The result is a black hole, a region surrounded by an event horizon, beyond which nothing can return. From the outside it appears simple, but in truth, it is one of the most complex structures allowed by physics. In a universe that contains extra dimensions, black holes become even more extraordinary. Their gravitational fields do not merely curve the 3 dimensions we move through, they extend into every dimension that space possesses. If our universe is a brane embedded in a higher dimensional bulk, then a black hole is not just a pit in the surface of that brane. It is a deep funnel that plunges into the bulk itself. Its gravity reaches far beyond our universe, probing directions that no light or matter can enter. This changes the meaning of a black hole completely. Instead of being a closed object, it becomes an interface. The intense curvature it produces could allow gravitational influence to flow freely into the extra dimensions. In some theoretical models, the The object we see as a black hole is only a slice of a much larger structure in the bulk. That larger structure might stretch through hidden dimensions like a dark thread passing through multiple layers of reality. These higher dimensional black objects are sometimes described as black strings or black brains. They are not confined to a single universe. They can extend across the bulk, connecting regions that would otherwise be completely isolated. Our brain intersects this higher dimensional object, and we observe the intersection as a black hole, but the true object exists far beyond our three-dimensional view. This possibility leads to a profound idea. When matter falls into a black hole in our universe, the gravitational field it generates may not remain entirely on our brain. Some of it could flow into the bulk, carried away through the higher dimensional structure of the black hole. This would mean that black holes are not only sinks for matter and energy in our universe, they are also channels through which gravity can escape. If gravity is leaking into extra dimensions anywhere, it is most likely to do so through black holes. They are the places where gravity is strongest and where the fabric of space is most distorted. The barrier between our universe and the bulk is thinnest there. Every black hole could be slowly draining gravitational influence from our cosmos, sending it into the hidden dimensions beyond. This does not mean black holes would disappear. They would still grow as they absorb matter, but the way their gravitational fields spread through space would be altered. Their influence on distant stars and galaxies might be slightly weaker than expected, because part of their gravity would be flowing elsewhere. The implications are enormous. If black holes are gateways to higher dimensions, then they are also gateways to other possible universes. Other brains could exist in the bulk, each carrying its own cosmos. The gravitational fields of those universes could pass through black holes and affect ours. In turn, the gravity generated by our black holes could reach into theirs. A silent exchange would take place, hidden from all forms of light and matter. This would mean that the growth and evolution of black holes in our universe might be influenced by structures we can never see. Their masses, their spins, and their mergers could carry subtle signatures of unseen neighbors in the bulk. The universe would not be an isolated arena. It would be part of a much larger gravitational ecosystem. Even the event horizon itself could be more than a boundary within our universe. It could be a surface where our brain intersects a higher dimensional object. Beyond it, space and time might continue into the bulk, following geometries that we cannot perceive. When we look at a black hole, we are not just looking at the end of a star. We may be looking at a tear in the fabric of reality, a place where our universe brushes against something far larger. Black holes may be the points where gravity escapes most freely. They may be the places where the hidden dimensions reveal themselves. They may be the true gateways between worlds. When gravity flows through a black hole into higher dimensions, it does not vanish. It changes where it lives. The gravitational field that once curved only our three-dimensional space becomes a distortion that spreads through the bulk. This means that a black hole could be far larger in the higher dimensional reality than it appears from our side. What we measure as a compact object with a certain mass could correspond to an extended structure whose true gravitational footprint reaches far beyond our universe. This has a powerful consequence. The strength of a black hole as we experience it may not tell the whole story. Part of its gravitational influence could be acting in directions we cannot measure. That would make black holes appear slightly less massive than they really are. Their true mass would be shared between our brain and the bulk. If this is correct, then black holes might be the clearest examples of gravity leaking away from our universe. They are not just extreme objects. They are boundary conditions between dimensions. When two black holes merge, the event is among the most violent in the cosmos. They release enormous amounts of energy in the form of gravitational waves. These waves are ripples in the fabric of space itself. They travel outward at the speed of light, carrying information about the collision. In a higher dimensional universe, those waves could spread into the bulk as well. Some of their energy would flow into hidden dimensions, leaving less behind in our own. This means that gravitational wave signals from black hole mergers could be slightly weaker than predicted by ordinary four-dimensional physics. The waves would lose energy not only by spreading through space, but by leaking into extra dimensions. The shape of the signal would be altered in subtle ways. Physicists analyze these signals with extraordinary precision. They compare the observed waveforms to detailed models based on Einstein's equations. Any discrepancy could reveal new physics. So far, the The data matches general relativity extremely well. This places tight limits on how much gravity can leak through black holes, but it does not rule out small effects. The fact that gravity behaves almost exactly as expected is itself remarkable. It suggests that if extra dimensions exist, they must be arranged in a way that hides their influence very effectively. But hiding is not the same as eliminating. The universe could be whispering secrets that we are only just beginning to hear. Another clue could come from the motion of black holes themselves. If gravity from other branes can influence ours, then black holes might experience tiny additional pulls. They could drift in ways that cannot be explained by visible matter alone. These motions would be extremely small, but over millions of years, they could accumulate. In the far future, when astronomers can track black holes with exquisite accuracy, such anomalies might become detectable. A black hole that seems to be tugged by nothing might be responding to mass in another universe. The idea is almost poetic. The darkest objects in our universe could be feeling the presence of worlds we can never see. Black holes may be listening to the gravity of the multiverse. The deeper scientists look into the mathematics of higher dimensional gravity, the more intricate black holes become. In four-dimensional space-time, a black hole is remarkably simple. Its entire external behavior is determined by just a few numbers. But in higher dimensions, new degrees of freedom appear. Horizons can stretch along hidden directions. Gravitational fields can wrap around extra dimensions. The interior geometry can become wildly complex. This complexity offers a potential solution to some of the most troubling paradoxes in physics. One of these is the information paradox. According to quantum theory, information can never be destroyed, but black holes seem to erase information when matter falls inside and then evaporates. In a higher dimensional universe, that information might not be lost. It could be stored in the bulk, carried away by gravity into dimensions we cannot observe. If this is true, then black holes are not cosmic erasers. They are redistributors of information. They move it out of our universe and into the hidden geometry beyond. This also means that the entropy of a black hole, which measures how much information it can contain, might reflect the size and complexity of its higher dimensional structure. The vast number of microscopic states that give rise to a black hole's entropy could live in the extra dimensions, not just on our brane. Every black hole could therefore be a library of hidden data, encoded in the shape of space itself. The interior of a black hole might also be radically different in higher dimensions. Instead of collapsing to a simple singularity, the geometry could open into the bulk. Space and time might continue in directions we cannot describe. The black hole could be a throat, leading into the deeper layers of reality. Whether such throats are stable, or whether anything could ever travel through them, is unknown. But the equations allow such structures to exist. They arise naturally when gravity is allowed to explore extra dimensions. This makes black holes not just objects, but transitions. They mark where our universe touches something larger. When we observe a black hole, we may be seeing only the surface of a far greater phenomenon. If black holes reach into the bulk, then they could also serve as anchors that tie our universe to the higher dimensional structure around it. Our brane may not be floating freely. It could be pinned, in a gravitational sense, by the presence of massive objects that extend into the extra dimensions. Black holes would be the strongest of these anchors. This could affect the stability of our universe. The shape and position of the brane in the bulk might be influenced by the distribution of black holes. As they move, grow, and merge, they could slightly shift the geometry of the bulk, changing how gravity behaves on the brane. The evolution of the cosmos would be linked to a deeper dynamical system that includes dimensions we cannot see. If other branes exist nearby, their black holes could interact with ours through the bulk. These interactions would not involve light or matter. They would be purely gravitational. Two black holes on different branes could orbit each other through the extra dimensions, even though their universes never directly touch. From our perspective, such interactions might look like unexplained changes in black hole behavior. A black hole might gain mass or spin without any visible accretion. It might drift or wobble for no apparent reason. These anomalies would be incredibly subtle, but they could be real. The idea that black holes could be influenced by invisible universes turns them into probes of the multiverse. They would be the only objects capable of sensing what lies beyond our cosmic horizon. In this way, gravity becomes a messenger. It carries information between layers of reality, and black holes are the nodes where those messages pass. Would you like me to continue to part 5 of this chapter? Part 5 completes this chapter. Even if black holes do act as gateways to higher dimensions, the universe remains protected by the nature of gravity itself. Nothing we know of can use these gateways to travel. They are not tunnels for matter or light. They are distortions of space that allow only the influence of gravity and perhaps information to pass. The bulk is not a place we can visit. It is a deeper layer of geometry that underlies everything we experience. Yet the existence of such layers would change how we think about reality. Our universe would no longer be the whole of existence. It would be a region, a surface, a domain embedded in something far larger. Black holes would be the deepest places in that domain, the points where the underlying structure is most exposed. As our observations grow more precise, black holes will continue to test our understanding of gravity. Every gravitational wave detection, every image of an event horizon, every measurement of a black hole mass adds another piece to the puzzle. We are slowly learning how gravity behaves under the most extreme conditions. If extra dimensions are real, their fingerprints will be written into these observations. The deviations will be small, the signals will be faint, but the universe is patient, and its story is long. Black holes may be telling us that space is not what it seems. They may be showing us that gravity does not belong to a single universe, and they may be hinting that the cosmos is woven from more dimensions than we ever imagined. Voices in the universe, yet they speak the deepest truths about the nature of reality. They are not vibrations in air or pulses of light. They are ripples in space-time itself. When massive objects accelerate, when stars collapse, when black holes spiral together, the geometry of space and time is disturbed, and that disturbance travels outward like waves across the surface of a vast cosmic ocean. These waves move at the speed of light, carrying with them a record of what created them. They encode the masses, the motions, and even the shapes of the objects that produced them. For a century, these waves existed only on paper, hidden inside Einstein's equations. They were predicted in 1916 as a consequence of general relativity, yet no technology was sensitive enough to detect them. The effect of a gravitational wave passing through Earth is incredibly small. It stretches and squeezes space by an amount far smaller than the width of a single proton. To measure such a change requires instruments of astonishing precision. That precision was finally achieved when detectors such as LIGO and Virgo began operating. These machines use long tunnels and laser beams to measure tiny changes in distance as a wave passes by. When the first gravitational wave was detected, it was not just a new kind of observation, it was a new sense. Humanity gained the ability to feel the trembling of space-time itself. What these detectors revealed was that the universe is far more violent than it appears. Black holes collide, neutron stars tear each other apart, massive stars collapse into ultra-dense remnants. Each of these events sends out a burst of gravitational waves that race across the cosmos. They cross billions of light years, passing through galaxies, through stars, through planets, and through our own bodies without leaving a trace until they reach a detector and briefly change the lengths of its arms. In a universe with only 4 dimensions of space-time, 3 of space and 1 of time, these waves behave in a very specific way. Their energy spreads out as they travel. The further they go, the weaker they become, because the same amount of energy is spread across a larger and larger spherical surface. This is why a wave from a distant black hole merger arrives faint and fragile after traveling for so long. But if space has more dimensions than we perceive, this spreading becomes more complex. Imagine sound traveling through air. In an open field, it spreads in all directions and quickly fades. But in a narrow hallway, it can travel much farther because it has fewer directions in which to spread. The same principle applies to gravity and to gravitational waves. The number of dimensions available determines how quickly a signal weakens. If our universe is a 3-dimensional brain embedded in a higher dimensional bulk, then gravitational waves are not restricted to our brain. they can move through the extra dimensions as well. As they travel, some of their energy can leak into those hidden directions. This means that from our perspective, the waves would appear to fade more quickly than expected. The waves would arrive weaker, their shapes would be altered. Their energy would not be conserved within our universe, because part of it would have flowed into the bulk. This is not a vague speculation. It is a direct consequence of extending the equations of general relativity into higher dimensions. When the geometry of space-time includes extra directions, the equations predict that gravitational disturbances can propagate into them. There is nothing in the mathematics that confines these waves to the brain. This makes gravitational waves one of the most powerful probes of extra dimensions. Light cannot leave our universe. Particles cannot leave. The electromagnetic force is trapped. The nuclear forces are trapped. But gravity is free. Gravitational waves are gravity in motion. They explore the full dimensionality of space. Every time a gravitational wave passes through a detector, it may be carrying with it a story not just of black holes and neutron stars, but of the geometry of hidden dimensions. Physicists have realized this and have begun to search for signs of dimensional leakage in gravitational wave data. They look for waves that fade too fast or that arrive with slightly distorted shapes. They compare observations to detailed models that assume only 4 dimensions. Any systematic difference could point to new physics. So far, the waves detected match Einstein's predictions with astonishing precision. This places strong limits on how large or how influential extra dimensions could be. If hidden dimensions exist, they must be small or warped in such a way that gravity remains mostly confined near our brain. But even a small deviation would be revolutionary, because it would mean that space-time is larger than we thought. It would mean that the ripples we detect are losing energy into unseen directions. It would mean that our universe is not closed. Every gravitational wave would be proof that gravity is exploring something beyond our world. Gravitational wave astronomy is still in its infancy. Only a few dozen events have been detected so far, but this number is growing rapidly. New detectors are coming online. Existing ones are becoming more sensitive. In the coming decades, thousands of gravitational wave events will be observed every year. Some will come from black hole mergers, some from neutron star collisions, some from exotic events we have not yet imagined. Each of these waves is a test. Each one is a probe of the dimensional structure of reality. If gravity leaks, the waves will tell us. The universe is whispering through space-time. We are finally learning how to listen. When a gravitational wave travels through ordinary 4-dimensional space-time, its behavior is governed by a simple but profound principle. Energy is conserved, and the wave spreads out in all directions available to it. In 3 dimensions of space, this means the wave expands outward, like the surface of a growing sphere. The energy is diluted across that expanding surface, which is why the signal weakens with distance. This pattern has been tested again and again with the gravitational waves we have observed. It fits Einstein's equations with remarkable accuracy. But if space has additional hidden dimensions, that spherical surface is no longer the whole story. The wave does not have to remain confined to the 3-dimensional shell that we perceive. It can spread into the bulk. The geometry of higher dimensional space gives the wave more directions in which to flow. As a result, the energy that remains on our brain decreases more rapidly. This effect would not necessarily be dramatic. The extra dimensions could be small, curled up in a way that limits how much energy escapes. They could be warped so that gravity is drawn back toward the brain. But even in these cases, a tiny fraction of every gravitational wave could still leak away. Over vast distances, that fraction could become measurable. One of the key signatures physicists search for is something called anomalous damping. This means that a gravitational wave fades more quickly than predicted by 4-dimensional physics. The shape of the wave as a function of time also changes. Its rise and fall, its oscillations, and its final ringdown all depend on how energy flows. Extra dimensions would leave subtle fingerprints in these patterns. Detecting such fingerprints requires extraordinary precision. The differences are small. They could be confused with noise or with ordinary astrophysical effects. This is why scientists combine data from many detectors and many events. They look for consistent patterns that cannot be explained by known physics. As the catalogue of gravitational wave detections grows, the statistical power of these tests increases. A single event might be ambiguous. Hundreds of events could reveal a clear trend. Thousands would be decisive. This is why future observatories are so important. Space-based detectors will be able to observe waves at lower frequencies, coming from massive black holes at the centers of galaxies. These waves travel for much longer times and across much greater distances. If any energy leaks into extra dimensions, these long journeys will amplify the effect. In some models, the leakage depends on frequency. High-frequency waves might behave differently from low-frequency ones. This would provide another way to identify hidden dimensions. By comparing how waves of different frequencies fade, physicists could infer the dimensional structure of space. Gravitational waves could become a kind of tomography of the universe. They would allow us to map not just where mass is, but how many dimensions it can influence. The idea that waves could vanish into hidden directions is unsettling. It means that even space-time itself is not fully contained within our universe. The ripples we detect might be only the surface of a deeper motion occurring in the bulk. Every merger, every collapse, every violent event in the cosmos sends out a signal that probes the boundaries of reality. We are listening not just to the universe, we are listening to the dimensions that hold it. Another way that extra dimensions could reveal themselves through gravitational waves is by changing how those waves are generated in the first place. When two black holes orbit one another, they lose energy by emitting gravitational radiation. This loss of energy causes their orbits to shrink, bringing them closer together until they finally merge. The rate at which this happens depends on how efficiently gravity carries energy away. In a universe with extra dimensions, gravity has more places to send that energy. Some of it would flow into the bulk. This would change how quickly the black holes spiral together. The entire dance would be altered. From our perspective, the inspiral would proceed at a slightly different pace than predicted by four-dimensional general relativity. This would affect the timing of the waves we observe. The frequency would increase faster or slower than expected. The moment of merger would arrive earlier or later. These are quantities that detectors can measure with great precision. Physicists use these signals to test gravity in the strongest fields ever observed. Black hole mergers push Einstein's theory to its limits. If extra dimensions influence gravity at all, their effects should be most visible here. There is also the possibility of entirely new types of waves. In higher dimensional theories, gravity can have additional modes of vibration. These modes would not exist in 4 dimensions. They could produce extra polarizations of gravitational waves, new ways in which space-time can stretch and squeeze. If detectors were to observe such polarizations, it would be a clear sign that space-time has more dimensions than we perceive. So far, only the 2 polarizations predicted by general relativity have been seen, but future detectors with better sensitivity could uncover more. The bulk itself could also have its own dynamics. Fields in the higher dimensions could interact with gravity, creating echoes or delays in gravitational wave signals. A wave might partially reflect off the geometry of the bulk and return to the brain. This would produce faint secondary signals following the main wave. These echoes have been proposed as a way to detect new physics near black hole horizons. Some theories predict that if space-time has a complex structure at very small scales, gravitational waves could bounce and interfere, creating a pattern of repeating pulses. Extra dimensions could produce similar effects. The search for such echoes is ongoing. The data so far is inconclusive, but the possibility is tantalizing. A single, clear detection would rewrite our understanding of space. Gravitational waves are not just messengers from distant cataclysms. They are probes of the deepest structure of reality. They tell us how space-time vibrates, and space-time may have more strings than we ever imagined. The most profound implication of gravitational waves traveling through extra dimensions is that our universe might not be the only one that produces them. If other brains exist in the bulk, their black holes and neutron stars would also generate gravitational waves. Those waves could propagate through the higher dimensional space and reach our universe. We would not see their light. We would not detect their particles, but we might hear their gravity. This means that some of the gravitational wave signals we observe could originate in other universes. They would arrive without any visible counterpart, no gamma rays, no optical flash, just a ripple in space-time with no obvious source in our sky. such events are already known. Many gravitational wave detections have no electromagnetic counterpart. They are assumed to come from black hole mergers, which do not produce light. But in a higher dimensional reality, some of these signals could come from entirely different brains. Distinguishing these possibilities is difficult, but there could be clues. Waves from another universe might arrive with strange distortions. Their amplitudes, frequencies, or arrival times might not match the distribution expected from sources in our cosmos. They could appear to come from empty regions of space. As detectors become more numerous, scientists will be able to triangulate the origins of gravitational waves more precisely. They will be able to locate events on the sky. If some signals consistently appear in regions with no galaxies, no matter, no possible sources, the question of other brains will become harder to ignore. The idea that we might hear the gravity of other universes is astonishing. It means that our universe is not silent. It is part of a larger gravitational conversation. Every black hole merger anywhere in the bulk could send ripples that wash across our brain. We may already be immersed in a sea of interdimensional gravity. Would you like me to continue to part 5 of this chapter? Part 5 completes this chapter. Even if we never directly confirm the existence of extra dimensions through gravitational waves, the search itself is transforming physics. It is forcing scientists to test gravity in regimes that were once purely theoretical. It is connecting the smallest scales of quantum geometry with the largest structures of the cosmos. Gravitational waves have given us a new way to see the universe. Not with light, but with the trembling of space-time. Through them, we can study black holes, neutron stars, and the fabric of reality itself. If that fabric has hidden layers, these waves will reveal them. The idea that gravity might leak into other dimensions is no longer just a mathematical curiosity. It is a testable hypothesis. Every detection, every waveform, every subtle deviation is a data point in a grand experiment. We are no longer asking only how gravity works. We are asking where it goes. If gravity truly moves through hidden dimensions, then the universe is far larger than it appears. Our brain is not the whole story. It is one surface in a multi-dimensional structure. Gravitational waves may be the threads that connect those surfaces. They may be the echoes of a multiverse, and we are just beginning to hear them. And leaking gravity eventually reaches the same unavoidable moment. It must be confronted by measurement. Nature does not bend to mathematical elegance. It responds only to what is real. If gravity truly spreads into unseen dimensions, then that fact must leave fingerprints somewhere in the universe. Subtle distortions in the behavior of matter, energy, and space-time that no ordinary explanation can fully erase. The challenge is that gravity is extraordinarily weak. It is the faintest of all the fundamental interactions. That weakness makes it exquisitely sensitive to new physics, but it also makes it incredibly difficult to measure. The smallest electromagnetic effect can overwhelm gravity at short distances. A single speck of dust can exert more force on a laboratory instrument than the gravitational attraction of a carefully positioned test mass. To test gravity at the scales where extra dimensions might reveal themselves, scientists must isolate their experiments from vibration, heat, air currents, magnetic fields, and even seismic activity. The most direct way to search for extra dimensions is to look for deviations from the inverse square law of gravity. In a universe with 3 dimensions of space, the strength of gravity decreases with the square of the distance. If you double the distance between 2 objects, the force drops by a factor of 4. This rule arises because gravity spreads out over the surface of a sphere as it moves away from its source. The area of that sphere grows with the square of its radius, so the force becomes diluted in exactly that way. But if space has more than 3 dimensions, the shape over which gravity spreads changes. The gravitational field would spread over the surface of a higher dimensional sphere. That surface grows faster than the surface of an ordinary sphere. As a result, gravity would weaken more rapidly with distance at small scales. The inverse square law would no longer be exact. Physicists have spent decades searching for this deviation. They use devices called torsion balances, which suspend tiny masses on thin fibers and measure how they twist in response to gravitational attraction. These instruments are sensitive to forces so small that they are almost beyond comprehension. A slight movement of air molecules, a tiny temperature change, or even the gravitational pull of a person walking nearby can spoil the measurement. By carefully controlling these experiments, scientists have been able to test gravity down to distances smaller than the width of a human hair. The results have been consistent with the inverse square law. Gravity behaves exactly as Einstein's theory predicts, down to these scales. This places strong limits on how large any extra dimensions could be. If they exist, they must be smaller than a few tens of micrometers, or else gravity would have already revealed their presence. Yet this is not the end of the story. The extra dimensions do not have to be simple or flat. They can be warped. In some brain-world models, the geometry of the bulk acts like a gravitational lens, focusing gravity toward the brain and hiding the influence of extra dimensions, even if they are relatively large. In these warped scenarios, gravity can remain nearly four-dimensional over a wide range of distances, only deviating at scales that are still beyond current experiments. Particle accelerators offer another way to probe these hidden dimensions. When particles collide at extremely high energies, they create new particles and fields. If extra dimensions exist, some of this energy could escape into the bulk. From the perspective of our detectors, it would appear as missing energy, momentum that simply disappears. The Large Hadron Collider was built in part to search for such effects. It smashes particles together at energies far higher than anything found in nature since the early universe. Physicists look for events where the total energy before and after the collision does not match. So far, no such anomalies have been confirmed. This tells us that if extra dimensions exist, they are either too small or too warped to be accessed by these energies. Yet even here, there is a catch. The energy scale required to probe extra dimensions depends on their geometry. In some models, it could be far higher than what current accelerators can achieve. In others, it might be just beyond our reach. The absence of evidence so far is not evidence of absence. The cosmos itself provides the largest laboratory of all. The expansion of the universe, the growth of cosmic structure, and the pattern of the cosmic microwave background all depend on how gravity behaves over billions of years and across billions of light years. If gravity leaks into extra dimensions, it could subtly alter these processes. Astronomers have measured the distribution of galaxies, the motion of clusters, and the fluctuations in the ancient light left over from the Big Bang with extraordinary precision. These observations match the predictions of standard cosmology remarkably well. This means that any leakage of gravity must be small enough not to disrupt the formation of the cosmic web or the expansion history of the universe. But again, small does not mean zero. Even a tiny effect, operating over cosmic timescales, could have profound consequences. The universe is a patient system. It amplifies the smallest differences over billions of years. The search for extra dimensions is therefore a search for whispers in the data. It is a hunt for patterns that do not quite fit, for tiny discrepancies that point to something beyond our current understanding. So far, the universe has been remarkably consistent with the idea that gravity behaves as if there are only four dimensions. But the door is not closed. It is only narrow. And behind that narrow door may lie a much larger reality. Beyond laboratory experiments and particle colliders, the most powerful tests of hidden dimensions come from the largest structures in the universe. Gravity is the architect of cosmic form. It shapes how matter clumps, how galaxies grow, and how clusters of galaxies evolve over time. If gravity leaks into extra dimensions, then these structures would carry the imprint of that leakage, like fossils embedded in the cosmic web. One of the most important tools for this search is the cosmic microwave background. This faint glow fills the universe and comes from a time when the cosmos was only a few 100,000 years old. At that moment, matter and radiation decoupled, allowing light to travel freely for the first time. The tiny variations in temperature and density that existed then have since grown into the galaxies and clusters we see today. These variations were shaped by gravity. If gravity behaved differently in the early universe because of extra dimensions, the pattern of the cosmic microwave background would be different. Satellites have mapped this ancient light with extraordinary precision. They have revealed a universe that is remarkably uniform, with fluctuations at the level of only one part in 100,000. The pattern of these fluctuations fits the predictions of a universe governed by ordinary four-dimensional gravity extremely well. This means that if extra dimensions exist, they did not dramatically alter gravity in the early universe. But subtle effects could still be hiding. The geometry of the bulk could have evolved over time. The way gravity leaks today might not be the same as it was billions of years ago. The early universe was hotter, denser, and more energetic. Extra dimensions could have been more active then, only to become more hidden as the universe cooled and expanded. Large-scale surveys of galaxies provide another test. Astronomers map the positions and motions of millions of galaxies, creating a three-dimensional picture of the cosmic web. This web formed because gravity pulled matter together from tiny initial fluctuations. The rate at which structures grew depends on the strength of gravity. If gravity has been slowly weakening because it is leaking into extra dimensions, then the growth of structure would be slightly slower than predicted by standard cosmology. So far, the data is consistent with ordinary gravity. But again, the uncertainties leave room for small deviations. The universe is complex. Many effects can mimic one another. Untangling them requires ever more precise measurements. Gravitational waves add yet another layer to this search. As discussed earlier, these ripples in space-time could lose energy to extra dimensions as they travel. By comparing the brightness and shape of waves from sources at different distances, physicists can test whether they fade in an unusual way. The first detections already place limits on how much leakage can occur. In all these cases, the story is the same. The universe has not yet revealed any clear evidence for extra dimensions, but it has not ruled them out either. The hidden dimensions, if they exist, are subtle. They are woven into the fabric of reality in a way that makes them difficult to detect. The search continues, not because physicists are stubborn, but because the stakes are enormous. Extra dimensions would change everything we think we know about space, time, and gravity. They would mean that our universe is part of something larger, and gravity would be the thread that connects it to that larger whole. As experimental limits tighten, physicists have learned something important about the nature of extra dimensions. If they exist, they are not simple. They are not just additional straight directions extending beyond the three we know. They are likely curved, warped, or compact in ways that make their effects difficult to detect. The universe is not just bigger than it looks, it is more intricately shaped than we can easily imagine. One of the most powerful ideas to emerge from this realization is that the bulk itself may have a complex geometry. In some brain-world models, the extra dimensions are not uniform. They can have regions where gravity is strong and regions where it is weak. Our brain could be sitting in a kind of gravitational valley where gravity is naturally concentrated. This would explain why gravity behaves almost exactly as if there were only 4 dimensions over a wide range of distances. Even though more dimensions exist, in this picture, gravity is not truly confined to our universe. It is simply guided by the shape of the bulk. The geometry acts like a funnel, keeping gravity close to the brain while still allowing it to explore the extra dimensions. This means that detecting extra dimensions may require probing the universe in ways that go beyond simple distance measurements. We may need to look for effects that depend on the curvature and topology of the bulk. These could appear in the way black holes behave, in the propagation of gravitational waves, or in the subtle evolution of cosmic expansion. Some theorists have suggested that the bulk could even have its own energy content, a kind of higher dimensional vacuum that interacts with gravity. This could influence how gravity leaks and how it is trapped. The expansion of our universe could be tied to the dynamics of this higher dimensional space. If this is true, then cosmology becomes a window into extra dimensions. The way the universe accelerates, the way structures form, and the way space-time ripples could all be shaped by the unseen geometry beyond our brain. Experiments and observations are now precise enough that these ideas are no longer purely speculative. They are being confronted by data. Every new survey, every new gravitational wave detection, every new test of gravity adds another constraint. So far, the universe has been remarkably conservative. It behaves as if it is 4-dimensional to a very high degree of accuracy. But the door to higher dimensions remains slightly open, and sometimes the smallest open door leads to the greatest discovery. The reason scientists persist in searching for extra dimensions despite the lack of direct evidence is that the idea solves problems that nothing else can. The hierarchy problem, the strange weakness of gravity compared to the other forces, remains one of the deepest mysteries in physics. Extra dimensions offer a natural explanation. Gravity is not weak because it is different. It is weak because it is diluted. This makes the search for extra dimensions not just an exotic quest, but a necessary one. If we abandon it, we are left with a universe that seems finely tuned for no reason. The strength of gravity appears to be set by a number that has no deeper explanation. Extra dimensions provide a way to make that number a consequence of geometry. The same is true for the unification of forces. The dream of physics is to find a single framework that describes all interactions. Extra dimensions allow forces to emerge from geometry. What we call electromagnetism, the strong force, and even gravity itself could be different aspects of motion in a higher dimensional space. Experiments have not yet confirmed this vision, but they have not destroyed it either. They have told us that if this picture is correct, it is subtle. The hidden dimensions are either very small, very warped, or both. This subtlety is itself a clue. Nature does not usually hide things without a reason. If extra dimensions exist, they may be arranged in a way that stabilizes the universe. They could be essential to the long-term behavior of space and time. The bulk might not be a passive container. It could be an active participant in cosmic evolution. Gravity could be the way information flows between the brain and the bulk. In this view, our experiments are not just probing our universe. They are probing the relationship between our universe and something larger. We are not just testing gravity, we are testing the shape of reality. Every experiment so far has delivered a humbling message. The universe is astonishingly consistent with the simplest picture of gravity we have. Einstein's theory, formulated more than a century ago, continues to describe reality with incredible precision. Yet this success does not close the door to deeper layers. It only tells us that if those layers exist, they are woven into the fabric of space-time in a way that makes them difficult to detect. The search for extra dimensions is therefore not a search for dramatic violations of known laws. It is a search for tiny imperfections, for slight mismatches between theory and observation. It is a search for places where gravity does not behave quite as expected. These places may be found in the earliest moments of the universe, in the most violent collisions of black holes, or in the faintest whispers of gravitational waves. They may be found in the slow drift of galaxies, or in the subtle bending of light. The universe is telling us something through its precision. It is telling us that whatever lies beyond our brain is hidden very well, but hidden does not mean absent. The idea that gravity leaks into extra dimensions remains one of the most compelling ways to understand its weakness. It connects particle physics, cosmology, and the structure of space itself into a single vision. Whether that vision is correct is still unknown, but the experiments continue, and the universe continues to answer, one measurement at a time. Of our universe, then the story of everything we see in the sky must be rewritten. Gravity is not just another force. It is the architect of structure. It decides where stars form, how galaxies spin, and whether matter clumps together or drifts apart. From the smallest moons to the largest galaxy clusters, gravity is the invisible thread that holds the cosmos together. If that thread is slowly unraveling, even by an imperceptible amount, then the entire history and future of the universe changes with it. In the earliest moments after the Big Bang, the universe was an almost perfectly smooth sea of hot matter and radiation. Yet tiny fluctuations existed, small variations in density that were only a few parts in 100,000. Those tiny differences mattered. Where matter was slightly denser, gravity pulled harder. Those regions grew, pulling in more matter and becoming the seeds of stars and galaxies. Without gravity, those fluctuations would have faded away. There would be no cosmic structure, only a thin soup of particles, spreading forever. If gravity was stronger in the past than it is today, then the early universe would have been more efficient at building structure. This could happen naturally if gravity is leaking into extra dimensions. At first, when the universe was young and compact, less gravity would have escaped. Most of it would have remained on the brane, strengthening the pull between particles. Over time, as space expanded and the geometry of the bulk evolved, more gravitational influence could flow away. The force would slowly weaken. This gradual change would be almost impossible to notice on the scale of a human lifetime. Even on the scale of the lifetime of a star, it would be tiny. But over billions of years, it could alter the architecture of the universe. Galaxies might form earlier and more efficiently than expected. Clusters of galaxies might be denser in the past. As gravity slowly loses strength, the formation of new large structures would slow down. The universe would shift from a phase of growth to a phase of dispersion. This could provide a new way to think about cosmic acceleration. Astronomers have discovered that the expansion of the universe is speeding up. Distant galaxies are not just moving away from us, they are moving away faster and faster. Something is overpowering gravity on the largest scales. This unknown influence is called dark energy, but that name hides ignorance rather than explaining it. If gravity is leaking into higher dimensions, then its ability to counteract the expansion of space would diminish over time. The universe would appear to accelerate, even if no new force existed. Space would stretch more easily as gravity slowly fades. In this view, dark energy is not a mysterious, repulsive force. It is the consequence of a weakening attractive one. The universe is not being pushed apart. It is losing the force that once held it together. This idea does not replace dark energy, but it offers an alternative interpretation. It suggests that the large-scale behavior of the universe may be governed by its connection to hidden dimensions. Our cosmos might be part of a larger gravitational system, one in which energy and influence can flow beyond the boundaries of what we see. If gravity escapes, it must go somewhere. The bulk would receive it. Other branes, other universes, could be gaining gravitational influence as ours loses it. A grand exchange could be occurring across dimensions, hidden from all forms of light and matter. This would mean that the fate of our universe is tied to the fate of others. The cosmic web, the vast network of galaxies and clusters, would evolve differently in such a scenario. In the standard picture, gravity continues to act forever. Even as the universe expands, galaxies remain bound internally. Stars orbit their galactic centers. Planets orbit stars. Structures persist. But if gravity weakens, even these bonds could eventually break. Over unimaginably long times, galaxies could dissolve. Stars could drift away from their galactic homes. Planetary systems could become unstable. The universe would not only grow empty, it would grow loose. This is not a prediction, it is a possibility. The mathematics of extra dimensions allows it. Whether nature chooses it is still unknown. The most haunting implication is that our universe may not be self-contained. We tend to think of the cosmos as everything that exists. But if gravity leaks into higher dimensions, then our universe is more like a region within something larger. The expansion of space, the growth of structure, and the fate of galaxies may all be influenced by that larger reality. We may be living in a universe that is slowly bleeding gravity into a hidden multiverse. If that is true, then every orbit, every star, and every galaxy is part of a deeper story. A story not confined to our sky. It is a story written across dimensions. If gravity is escaping our universe, then its loss would not be uniform everywhere. The geometry of space and the distribution of mass would determine where gravity leaks most strongly. Regions with intense gravitational fields would be the most likely places for energy to slip into the bulk. That means galaxy clusters, dense cosmic filaments, and especially black holes would be the primary outlets through which gravity drains away. This creates a universe that is not just expanding, but dynamically reshaping itself as gravity redistributes across dimensions. The densest regions would slowly lose some of their binding force. Over time, clusters of galaxies might become less tightly bound. The orbits of galaxies within clusters could widen. The cosmic web itself could stretch more than expected, becoming more diffuse as gravity gradually weakens in the places where it once dominated. This process would not be chaotic. It would be governed by the equations of higher dimensional gravity. The rate at which gravity leaks would depend on the curvature of the bulk and the shape of the brane. In some models, gravity is loosely bound to our universe, hovering near it but not permanently attached. In others, the geometry of the extra dimensions acts like a trap, keeping gravity close while still allowing a slow escape. If the escape is slow enough, it would take billions of years to produce a noticeable effect. That is precisely the timescale over which cosmic acceleration becomes important. The coincidence is striking. The universe began to accelerate only relatively recently in cosmic history. For most of its existence, gravity dominated. Galaxies formed, clusters grew. Then, a few billion years ago, the expansion began to speed up. This could mark the point at which gravity started leaking more efficiently into the bulk, perhaps as the geometry of extra dimensions evolved. In this view, the acceleration of the universe is not driven by a new force, but by a change in the way gravity behaves across dimensions. The large-scale distribution of matter could reveal this history. Astronomers observe that the universe contains vast empty voids surrounded by filaments of galaxies. These structures grew under the influence of gravity. If gravity was stronger in the past, these filaments would be more pronounced. If it weakens over time, their growth would slow. Careful measurements of galaxy clustering over different eras of cosmic history could reveal whether gravity has changed. So far, the data is consistent with ordinary gravity, but the uncertainties are large enough that small deviations could still be hiding. Another clue could come from the motion of galaxies within clusters. If gravity is slowly weakening, then galaxies should gradually drift apart. Their velocities could be slightly higher than expected for a given amount of visible mass. This effect is often attributed to dark matter or dark energy, but gravity leakage could contribute as well. The universe might be telling us that it is not isolated. It might be interacting with something larger through gravity. Every galaxy could be part of a multi-dimensional dance. The idea that gravity could escape into extra dimensions also changes how we think about the long-term future of the cosmos. In the standard picture, the universe expands forever, but gravity continues to operate locally. Galaxies drift apart from one another, yet stars remain bound to galaxies, and planets remain bound to stars. Structure survives even in a cold and dark future. But if gravity weakens over time, the story becomes far more fragile. Over immense stretches of time, the bonds that hold galaxies together could loosen. Stars might slowly drift out of their galactic neighborhoods. The gravitational glue that keeps clusters intact could weaken until the clusters themselves dissolve. The universe would not just become empty, it would become unbound. Even smaller systems could be affected. On unimaginably long timescales, planetary orbits might slowly widen. Moons could drift away from their planets. Eventually, even the delicate gravitational dance that keeps atoms inside stars could be altered, although that would occur far beyond any timescale we can meaningfully imagine. This scenario is not required by current observations. It is simply allowed by the mathematics of extra dimensions, but it reveals how profoundly gravity connects everything. A small change in its behavior, even one that is almost invisible today, could reshape the fate of all things. There is also a deeper implication. If gravity is escaping our universe, then energy is not strictly conserved within it. The total gravitational energy of our cosmos would be slowly flowing into the bulk. This does not violate any fundamental law, because the higher dimensional system as a whole could still conserve energy. But from our perspective, the universe would be an open system, exchanging energy with something beyond. This means that our universe is not a closed book. It is part of a larger story. The mass and energy we see could be interacting with unseen realms through gravity alone. Other universes could be gaining what we lose. Their gravity could be strengthening as ours fades. The multiverse, if it exists, would not be a collection of isolated bubbles. It would be a connected gravitational network. Gravity would be the thread that binds it. If gravity connects multiple universes, then the structure of our cosmos could be influenced by things we can never observe directly. Invisible brains, floating in the bulk, could contain vast amounts of matter and energy. Their gravitational fields could reach into our universe, subtly shaping the motion of galaxies and clusters. This idea offers a new way to think about dark matter. Dark matter is inferred from its gravitational effects. It does not emit light. It does not interact electromagnetically. We see it only through the way it pulls on visible matter. If other universes exist nearby in the bulk, their mass could influence our brain through gravity. From our perspective, this would look exactly like dark matter. The galaxies of another universe could be tugging on ours. Their clusters could be shaping our cosmic web. We would never see them, but their gravity would be real. This does not mean that dark matter is explained by other universes. Many models of dark matter exist, but the possibility highlights how extra dimensions could make parallel realities physically relevant. The same could be true for dark energy. The expansion of our universe could be influenced by the distribution of energy in the bulk. The geometry of extra dimensions could be evolving, pulling our brain in ways that look like a repulsive force. In this picture, cosmology becomes a study not just of our universe, but of the higher dimensional environment in which it is embedded. We are not just mapping galaxies, we are mapping the shape of hidden space. Would you like me to continue to part 5 of this chapter? Part 5 completes this chapter. If gravity is escaping our universe, then the most important thing to understand is not just how fast it is leaking, but where it is going. The bulk may not be empty. It could contain other brains, other universes, each evolving under its own laws of physics. Gravity could be the only force that allows these worlds to influence one another. This would mean that the multiverse is not a collection of isolated bubbles. It is a gravitationally connected system. Energy, information, and structure could be shared through the geometry of higher dimensions. Our universe could be gaining and losing gravity as part of a larger cosmic balance. The weakness of gravity would then be more than a mystery. It would be evidence of connection. We would not be living in a lonely cosmos. We would be part of a vast hidden architecture, held together by a force that reaches farther than light. Gravity may not belong to us alone. It may belong to all universes. Beyond the boundaries of our universe, then the idea of a multiverse stops being a metaphor and becomes a physical structure. Our universe would not be a closed bubble drifting in nothingness. It would be a region embedded in a higher dimensional space, connected to other regions by the geometry of gravity itself. What we call parallel universes would not be sealed off from one another. They would be part of a single gravitational system. In this picture, gravity is not just the force that pulls apples toward the ground and keeps planets in orbit around the sun. It is the one interaction that is aware of the full dimensionality of reality. Every time a mass curves space, it is not only shaping the 3 dimensions we see, it is also shaping the hidden directions that lie beyond our perception. That curvature can propagate through the bulk, reaching other brains that carry their own universes. This means that every star, every galaxy, and every black hole contributes to a vast multidimensional gravitational field. Our universe does not live inside empty space. It lives inside a complex gravitational landscape created by all universes together. If another brain exists nearby in the bulk, its galaxies would be curving the same higher dimensional space that our galaxies do. We would never see their light, because light cannot leave its brain. We would never detect their particles, because matter is confined. But we would feel their gravity. This offers a radical way to think about some of the biggest mysteries in cosmology. Dark matter, for example, is known only through its gravitational effects. It does not emit or absorb light. It does not interact with ordinary matter except through gravity. If other universes exist in the bulk, their mass could influence our brain gravitationally. From our perspective, this influence would look exactly like dark matter. The galaxies of another universe could be shaping the rotation curves of our galaxies. The clusters of a hidden brain could be tugging on our cosmic web. We would attribute these effects to invisible matter within our universe, never realizing that the source lies beyond it. The same could be true for dark energy. The expansion of our universe might be influenced by the geometry of the bulk and by the distribution of energy on other brains. If the bulk is stretching or evolving, it could pull on our brain, driving cosmic acceleration. What we interpret as a mysterious force-filling space could instead be a response to higher dimensional dynamics. In such a reality, cosmology becomes a branch of interdimensional physics. The expansion history of our universe would not be determined solely by what is inside it. It would also depend on what lies outside. The weakness of gravity would then be one of the most important clues we have. It would tell us that gravity is not confined to our universe. It is shared. It is diluted across dimensions. The reason gravity feels so faint compared to the other forces is not that it is inferior. It is that it is doing far more work. It is holding together not just one universe, but many. This changes how we think about the ultimate structure of existence. The multiverse would not be a chaotic collection of disconnected bubbles. It would be a gravitationally unified system. Black holes in one universe could influence the geometry of space in another. Galaxy clusters on different branes could participate in the same, higher dimensional cosmic web. Reality would be layered, but connected. Even the birth of universes could be part of this structure. In some theories, new branes can form in the bulk, like ripples in a higher dimensional fabric. These branes could carry their own universes, complete with particles and forces. Gravity would immediately connect them to the existing network of worlds. The multiverse would be dynamic, evolving, and interactive through gravity. We would be living in a universe that is not alone, but also not isolated. Every gravitational interaction would be a whisper from this greater whole. The stars in our sky would be responding not only to the mass we see, but to the unseen architecture of higher dimensional space. The universe would be far more alive than we ever imagined. If gravity binds multiple universes into a single higher dimensional structure, then the idea of isolation becomes an illusion. Our cosmos would not be a lonely island in an infinite void. It would be one shore along a vast multidimensional sea. The waves of that sea would be made not of water, but of curvature. Every mass would send ripples through the bulk, and those ripples would touch worlds we can never see. This means that when galaxies form in our universe, they are not just responding to the gravity of nearby matter. They are also embedded in a gravitational environment shaped by everything that exists across dimensions. The large-scale structure of our cosmos might be subtly influenced by the presence of other branes, their clusters of galaxies, and their black holes. Over billions of years, these influences could accumulate. They could shift the way our universe expands. They could alter the growth of cosmic structure. The history we reconstruct from telescopes might be only a partial record of the true forces at work. In this view, gravity becomes a universal currency. It is exchanged between branes. Energy flows through it. Geometry evolves because of it. The bulk becomes a kind of gravitational marketplace where universes trade influence. The conservation laws we rely on would still hold for the entire higher dimensional system, but not necessarily for each individual universe. Our cosmos could be gaining or losing gravitational energy as part of a larger balance. This would not violate any fundamental principle. It would simply mean that our universe is not closed. The implications reach even into the deepest questions about origin. The Big Bang might not have been the absolute beginning. It could have been the formation of our brane within the bulk. Other branes might have formed before it, or after it. Gravity would link them all, weaving a timeline that extends beyond our own. Even the ultimate fate of our universe would be tied to this larger system. Whether space expands forever, collapses, or settles into some steady state could depend on what happens in the bulk. A change in the distribution of mass across dimensions could alter the geometry that governs our expansion. We are used to thinking of the universe as a self-contained story, but gravity suggests something else. It suggests that we are reading only one chapter of a much larger book. In a multiverse connected by gravity, even the concept of distance becomes ambiguous. Two galaxies that appear billions of light years apart in our universe might be separated by a much shorter path through the bulk. The geometry of higher dimensional space could fold and curve in ways that bring distant regions close together. Gravity would follow those paths. It would take shortcuts through hidden dimensions, linking places that seem forever separated in our sky. This could explain why gravity behaves so differently from the other forces. Electromagnetism, the strong force, and the weak force are confined to the brane. They must travel the long way around, across the visible dimensions. Gravity is free to explore the full geometry of space. It can find the most efficient routes through the bulk. As a result, its influence spreads out and weakens in our universe, even though its total strength across all dimensions may be immense. This picture turns the weakness of gravity into a sign of its reach. It is weak here because it is strong everywhere. It also suggests that the multiverse is not a set of separate realities, It is a single gravitational organism. The curvature created by one universe contributes to the shape of the whole. Every brane participates in the same higher dimensional geometry. If this is true, then black holes are not just endpoints of matter, they are nodes in the gravitational network. Their immense mass creates deep wells in the bulk, influencing not only our universe, but others as well. A black hole on one brane could affect the geometry near another brane, altering the way gravity behaves there. The birth and death of stars, the mergers of galaxies, and the collisions of black holes would all send ripples through this network. The multiverse would be alive with gravitational motion. We would be living in a reality that is constantly shaped by unseen events in unseen worlds. Gravity would be the medium through which all of it is communicated. If gravity truly connects universes, then every gravitational interaction becomes part of a vast, multi-dimensional architecture that extends far beyond what we see. The pull between two atoms, the orbit of a moon, and the motion of a galaxy are not isolated events. They are expressions of a single, higher dimensional geometry that spans many realities at once. Our universe is not suspended in emptiness. It is embedded within a gravitational landscape, shaped by all universes together. This means that the bulk is not a passive void. It is a dynamic structure that responds to mass and energy wherever they exist. When a star forms in our universe, it curves not only the three dimensions of space around it, but also the hidden dimensions that thread through the bulk. That curvature spreads outward into realms we cannot perceive, gently reshaping the gravitational environment of other branes. In return, the mass and energy of those branes shape the bulk in ways that feed back into our own universe. The result is a multiverse that behaves like a single connected organism. Each universe is a cell within it, carrying its own matter and light, but sharing a common gravitational skeleton. Gravity becomes the nervous system of this organism, transmitting influence across dimensions and allowing distant realities to affect one another. This interconnectedness has profound implications for the nature of physical law. The constants that govern our universe may not be fixed by chance. They may be determined by where our brain sits within the higher dimensional geometry. Just as the strength of gravity on Earth depends on the mass of the planet and its position in the solar system, the strength of gravity in our universe could depend on its position in the bulk. Some regions of higher dimensional space might naturally amplify gravity on a brane, while others weaken it. Some might stabilize physical laws, while others make them chaotic. Our universe could exist where it does, because only there can long-lived structures form. Stars, galaxies, and life itself might be consequences of geometry far beyond our sky. In this picture, the multiverse is not random, it is structured. Branes could drift through the bulk, pulled and pushed by gravitational gradients. Some might collide, others might merge. New universes could be born from these interactions, while old ones might fade as their gravity disperses. The evolution of our universe would then be tied to a much larger history. The Big Bang might not have been the absolute beginning. It could have been a local event within a vast multidimensional process. Our universe might have formed from the collision or separation of branes, its initial conditions shaped by forces outside it. Even the future of our cosmos would depend on this deeper structure. Whether our universe expands forever, collapses, or tears itself apart could be influenced by the behavior of the bulk. A change in the distribution of mass across dimensions could alter the geometry that governs our expansion. Gravity would be the mediator of all these effects. It would carry the imprint of distant universes in the way it behaves here. The slow drift of galaxies, the shape of cosmic expansion, and the stability of physical laws could all reflect the hidden gravitational environment beyond our brane. We may already be living inside this system without realizing it. Every gravitational measurement we make could be sensing not just our universe, but the presence of others. The multiverse would not be a collection of unreachable worlds. It would be a single gravitational entity, with many layers. Reality would be deeper than space and time alone, and gravity would be the thread that binds it all together. If gravity truly weaves together multiple universes, then the meaning of existence itself changes. Our universe would no longer be a solitary stage floating in nothingness. It would be a region inside a vast gravitational structure that spans dimensions and realities. Every star, every galaxy, and every black hole would be part of a much larger architecture that cannot be seen, but can be felt. In this deeper view, gravity is not merely a force. It is the geometry of connection. It is the mechanism by which every universe influences every other, even if they never exchange light, matter, or information in any conventional sense. The bulk becomes a living framework of curvature, constantly reshaped by the mass and energy of all brains together. Our universe is embedded within that framework, responding to it as much as it shapes it. This means that the weakness of gravity is not a mystery to be solved, but a message to be understood. Gravity appears faint here because it is not focused here alone. It is distributed across a greater space, across hidden dimensions, across multiple realities. The pull we feel is only the local shadow of a force that extends far beyond our horizon. The stars in our sky are not only bound to one another, they are part of a higher dimensional gravitational web. The black holes at the centers of galaxies may be anchoring our universe to the bulk, tying it to the deeper structure that contains many worlds. Their immense mass creates distortions in higher dimensional space that may influence other brains as much as they influence ours. In such a reality, the formation of galaxies, the expansion of the universe, and even the stability of physical laws may be shaped by unseen neighbors. Other universes could be pulling on ours through the geometry of the bulk. Their distribution of matter could be affecting our cosmic acceleration. Their black holes could be subtly altering the way gravity behaves in our sky. We may already be living inside a multiverse that is not separate, but shared. This does not diminish our universe, it makes it more profound. Our history, from the Big Bang to the formation of stars and planets, may be part of a grander cosmic evolution that spans dimensions. The birth of our universe might have been influenced by events in the bulk. Its future might depend on how the higher dimensional structure changes. Even the ultimate fate of everything we know could be linked to what happens beyond our cosmic horizon. Whether space expands forever, collapses, or reaches some stable state may depend on how gravity is distributed across the multiverse. The universe, in this view, is not a closed book. It is a chapter in a story written across dimensions. We have only just begun to read it. Every gravitational wave, every orbit, every motion of a galaxy carries information about that deeper story. Gravity is the only force that knows the full shape of reality, and it is whispering to us, even now, that the cosmos is far larger than we ever imagined. Perhaps gravity is not weak. Perhaps it is simply reaching into other universes, binding them all into one extraordinary whole.